Hi, my name is João Rodrigo Andrade, and I present the work an in-house finite volume analysis to predict the heat-affected zone in a TIG welding. This work was developed by Stefani, João Rodrigo, me, Fran, Sérgio, Luiz, Eduardo, Louriel, and Ruham. All the authors are from Federal University of Uberlândia. First of all, the summary is given by first the introduction, the energy equation, numerical model, objectives, simulation and experimental setup, the result and discussion, further works, and finally the acknowledgement. It's known that the naval, the automotive, and oil industry highly depend on welding process. For instance, in the assembling stage, there is a constant need to join parts of different materials and shape. Also, it's known that the manufacturing of metal components has been investigated through additive manufacturing technology. Among the main types of welding, the TIG procedure is given by an arc generated between a non-consumable tungsten electrode and the workpiece. Its main advantage is related to higher quality when compared to other procedures, for example, the MIG-MAG. In this figure, right here in this slide, from Silva et al., we can see a mechanized TIG process which was applied to weld the root pass of a pipeline joint. The components of the TIG process are the Y feeder and the TIG torch, as can be seen in the following figure. The main reason for its good welding quality relies on the heat input that can be controlled independently from the filler material, which results in a low defect incidence. The limitation of the TIG procedure regards the fact that it's hard to achieve higher productivity. However, recent works have shown that this drawback can be solved. And here we state that a thermal analysis of weld procedure starts at the fusion zone, the FZ. This area is constituted by the melted material. In the heat-affected zone, there are changes in the material microstructures. The farthest area from the weld is designated as base material, base metal, and remains unchanged. That means phase transformation does not happen as a result of processing. Then there are temperature gradients in the base metal that promote different microstructural regions. Some authors show that the brittle phase can occur in the welding region. And Chen et al. Proves that growth also happens, which is deleterious for the material integrity. In this figure that you can see right here, we can find three main regions: the fusion zone, where the material phase changes; the heat-affected zone, where change the material microstructure happens; and the original joint. Main definition can be found for the heat-affected zone. For instance, O'Brien and Guzman indicates that the heat-affected zone consists of a region near the FZ zone, the fusion zone, where microstructural change occurred and can be observed through chemical etching or measurement of the hardness profile. Different definitions given by other authors can be found as well. For instance, Coe and Lippold. Lippold claims that for the ion-carbon diagram, the Hess temperature range varies between 727 degrees, which corresponds to the lowest austenitization temperature, and the solidus temperature, which is the maximum where the alloy is still a solid. This figure right here represents the ion-carbon diagram and the related region in the welding process. We can, for instance, observe a sketch of the Hess zone, which is composed by fine and coarse grain. It's known that microstructural chains involve phase transformation, and all these transformations are not instantaneous. That means that time is really important in order, for instance, to calculate the austenite phase fraction, F. For example, here we can note this figure that the behavior of temperature in a given proposition along the simulation time. Firstly, the temperature is 25 degrees Celsius. Then it begins to warm due to the approximation of the welding heat source. Finally, it reaches its maximum peak and the temperature begins to fall. The gamma phase fraction can be calculated with the modified GMA equation. Here we consider the transformation kinetics. The first input in this equation is the thermal cycle. After the austenitization interval, the cooling rate is the main factor to determine the final microstructure. The GMA equation is shown right here, right? Write this equation right here, where K and N are modal coefficients. R is the universal gas constant and Q is the activation energy. By means of numerical simulation, enhancement in the understanding of the main characteristics of the welding procedure can be reached. In order to use a simulation, this kind of simulation in our work, we have employed the three-dimensional heat equation presented right here, for which the enthalpy enthalpy function H considered is defined by the following equation right here. In order to solve the presented equations, it was necessary to define boundary and initial conditions. Therefore, convection and radiation effects were imposed, as well as a moving heat source which described the thermal effect of welding. And they are shown right here, these equations. Concerning the welding boundary condition, the heat flux is given by a homogeneous heat surface distribution limited by a circular area on the top surface of the geometry of the workpiece. The considered thermal efficiency eta was based on the following equation right here, and the welding heat source radius R was established by this equation, this equality right here. Further information about the computational code is given below. We employ the MATLAB algorithm, which can be found in this link right here. And it's open, it's free. The finite volume method was applied with a first-order explicit Euler method. The diffusive term was approximated by the central difference scheme. In the present paper, we propose to consider, besides the critical temperature of 727 degrees Celsius, the austenite phase fraction to delimit the heat affected zone by employing the GMA equation. An in-house MATLAB-based code was developed and qualitatively validated with experimental results for the TIG process in steel as material. In further work, this code also will be adapted to allow other important analyses for welding and also for additive manufacturing process. So then, an autogeneous welding process was simulated on a carbon steel plate with the following dimensions, displayed in this figure. The welding source path is given by a straight line in the workpiece center line. and it's shown right here. The process parameters applying the present work are presented by the following three tables. And the welding power P can be calculated multiplying the current I by voltage U, since both are near constant. Mesh refinement was also applied in the region close to the heat source path. The grid details can be seen in the following figures. Gradual refinement was applied. A mesh with near 330,000 elements was applied. The minimal volume dimension is given by 2.5 to the minus 10 millimeters. Two different methodologies for the heat effective zone delimitations are obtained. For figure A, in the left side, we used a critical temperature. In figure B, on the right side, we applied the austenitization phase fraction by employing the GMA equation. For the critical temperature criterion, the head starts at 5.77 millimeters from the weld center line. However, by considering F, it reaches about 1% at 5.76 millimeters and ends with a 99% at 4.61 millimeters from the welding center line. Then the criterion usually applied considering only the critical temperature is already sufficient to limit the largest region where microstructure changes could occur. However, the identification of regions with lower and higher degree of austenitization is also important for welding, since if the component is subjected to a steep cooling rate, the percentile of brittle phase, such as martensite, can be computed, since it's proportional to the austenite phase fraction. From experimental results, we note that the numerical model can predict the Hess boundary by approximately 90%. Based on this discussion, we can conclude that the austenite phase fraction can be used as well as the critical temperature to delimit the Hess, but there is not a significant difference in practice when using only the critical temperature. Therefore, the implementation of the GMA equation in a numerical model is more relevant to identify the regions subject to a higher degree of phase transformation and consequently higher probability of brittle phase, which is very important for this kind of analysis. Finally, the comparison of experimental and numerical results allowed the validation of the in-house finite volume code developed in the present work. So, as further work, we expect to map the austenitization regions that had higher cooling rates in order to quantify the final microstructure after cooling the workpiece. We also intend to optimize the welding parameters in order to avoid deleterious microstructures. And finally, we aim to develop new heat sources that better represent the process characteristics. So, I would like to thank you very much for your attention. This work was developed by the following researchers. And here you can find the presentation reference. Thank you very much.